Let me start this lesson by wishing you all a big congratulations and thank you for journeying all the way to the end of Module 1 with me. After today's lesson, you will have reached the first milestone in this analytical journey you've undertaken. Often after working hard to improve oneself, it is natural to feel tired and lose motivation. Therefore, I want to use this time to talk about the next step in the journey and goal setting. Professional athletes and successful business people will tell you that you need to set goals on a number of levels. The first level is to create a long-term or big picture goal. What is it you want to achieve in the next 10 years? For myself, I want to keep on improving my statistical skills in order to become an expert in the field. The second stage is to break the bigger goals into more sizable chunks, like a course through SAS Academy, and then a module of the course. Lastly, you need to put a realistic plan into action. How do you intend to reach these smaller goals? And with that thought, a really big welcome back from all of us here at SAS Academy, where we are here to help you learn the skills you need to succeed today. Speaking about goals, a quote I quite resonate with by Orison Martin says, "All who have accomplished great things have had a great aim, have fixed their gaze on a goal which was high, one which sometimes seemed impossible." In case you forgot, the voice you're hearing now is not Marlies. My name is Nina Smith, and I am the presenter of this course. This is your professional diploma course in statistical analysis lesson 8, where we will continue exploring hypothesis testing. Today's lesson will continue the concepts of hypothesis testing we introduced in lesson 7. We will explore and investigate hypothesis testing concepts surrounding small and large samples. By the end of this lesson, you will be able to identify which procedure to use for a variety of different scenarios. Lesson 8 will end by tying together the practical concepts explored throughout Module 1 and offer some new tips and tricks for data management in SAS Studio not yet explored. Let's explore the topic of large sample hypothesis testing by adding some more tools to our hypothesis testing toolkit. In contrast, if our hypothesis states that two groups differ but does not indicate directions, that is, which is greater, we're dealing with a two-tailed test, and the rejection region is located in both tails of the sampling distribution. We're dealing with a large sample, meaning we apply the central limit theorem. The normal distribution shape according to the theorem stays the same. Therefore, our critical values will always remain the same at the various confidence levels. A two-tailed test allocates half of the alpha to testing the statistical significance in the upper tail of the normal distribution, and half of your alpha to testing the statistical significance in the lower tail of the normal distribution. Therefore, if we are using a significance level of 0,05, 0,025 is in each tail of the distribution of the test statistic, and the critical value is plus minus 1.96. A one-tailed test, on the other hand, allocates the entire alpha to testing statistical significance in either the upper or lower tail of the distribution. Therefore, with a significance level of 0.05, 0.05 will be in either the upper or lower tail of the distribution, and the test statistic will be plus minus 1.645, depending on the test. For the two-tailed hypothesis, we made the decision to reject the null hypothesis if the test statistic fell in the rejection region that are located in the upper and lower tails of the sample distribution. For a one-tailed hypothesis test, the rejection region is located in either the upper or lower tail of the sampling distribution, depending on if we want to determine if the population mean is greater or less than a given quantity. Therefore, the alternative hypothesis states that the population mean is less than a given quantity, and the test statistic lies in the lower tail rejection region. the null hypothesis is rejected. We have learned that the test statistic measures the degree of agreement between a sample of data and the null hypothesis. Previously, we defined the general formula for the test statistic to be the hypothesized parameter divided by the standard error of the sample statistic. Because we have a large sample, we can apply the central limit theorem and assume normality. For the normal distribution, we use the variable z as the test statistic for where the population standard deviation is known. The formula for the z-test statistic is the following, where x is sample mean, mu is the population mean, s is the population standard deviation, and n is sample size. If the test statistic lies in the rejection region, meaning if it's past the critical value, we would reject the null hypothesis and say that the null and alternative hypothesis is more likely not the same. The last step is to either reject the null hypothesis and accept the alternative hypothesis, or to not reject the null hypothesis. Remember, all the summary notes and slides are available in your toolkit and would really be worthwhile to keep as a resource at your fingertips beyond this course. But no sneak peeks, the lesson notes will only become available after you have attended your class or caught up with the lessons. These will also help you prepare for your assignments. Until now, we've only conducted hypothesis testing on larger samples. But what happens when you have a smaller data set that contains less than 30 observations? When we have a small sample with less than 30 observations, the central limit theorem does not apply, and so we cannot assume that the distribution we're dealing with is normally distributed. Therefore, we have to apply stricter assumptions in the form of a t-test to ensure statistical validity to the testing procedure. The t-test, or student's t-distribution, is similar in shape to the normal distribution. But we use the t-test for smaller sample sizes because we don't know what the true standard deviation of the sample is, if we cannot assume normality. In contrast, if the population is large enough and the distribution is known, we also know what the true standard deviation is. Let's investigate the case with a small sample hypothesis test with a single population mean, where the population standard deviation is unknown, with a sample standard deviation of S. Our test statistic would follow the student's t-distribution with degrees of freedom equal to the number of observations in the sample, called n-1. The formula for the student's t-distribution is the observed mean minus the hypothesized value of the population mean divided by the standard error of the mean. Let's head over to SAS Studio again to put the skills gained to practical use. In the first topic, we investigated a large sample hypothesis test. Now, for the first demo of the day, we're going to investigate a small sample hypothesis test using a t-test. And the specific example we will look at is called paired t-test. So let's first input the data. We can call the data pressure, and we input the systolic blood pressure variables. Systolic blood pressure variable before and after an intervention. This data set contains paired measures of systolic blood pressure before and after an intervention took place. So this line tells SAS Studio that we are reading in the variables SBP before and after in the data set. The two @ quoting from SAS documentation holds an input record for the execution of the next input statement across iterations of the diagnostic. The line holds specifier is called double trailing. So in other words, these two @ tell SAS that it needs to read these two measures as if it is from the same item, or in this case, the same patient. So this score is the systolic blood pressure before the intervention, and the next score is the systolic blood pressure after the intervention. And only once SAS has read both of these values, it will read the next patient's systolic blood pressure before and after the intervention. Let's input the rest of the values for the rest of the patients. Now that we've inputted all the data points and we've told SAS Studio that it needs to run the above code, I've also included a comment here that reads that the SBP measure before and after has to do with systolic blood pressure, so that we can remember that. So let's run this code to explore the output in table format. In the output window, we notice the systolic blood pressure before and after. But where is this first SBP measure? We're missing a measure, the value 128. So why did that not read in? Let's see here. So the problem was that the space was a tab, not a single space. So we note that each of the spaces in between the values need to be single spaces, not tabs. The formatting needs to be the same throughout the data lines. Okay, and now we want to figure out if the intervention actually had an impact on the systolic blood pressure of the patients. And the way that we will do that is by conducting a paired proc t-test. We conduct a t-test because this sample is small. It has less than 30 observations. There are in fact 12 patients contained in the sample, so it is quite small. I've also just made a comment that this example or data is taken from the SUGI Supplemental Library User's Guide to give credit where it's due. So let's input the proc t-test statement now on the pressure data set. This is a pair t-test because our measures are paired. The systolic blood pressure before is related to the systolic blood pressure measure after. So we've gone about this a little bit backwards, but we have to now think about what is the null hypothesis. What is the hypothesis that we're trying to disprove? A null hypothesis in a paired t-test will always state that the mean of the first sample, so the mean of our systolic blood pressure before these measurements or this variable, equals the mean of the systolic blood pressure after a stimulant was given or after the intervention took place. So we want to determine if they are the same. That is the null hypothesis and the alternative hypothesis. The alternative hypothesis state that the two will be different, and the way that we know if they're the same or if they're different, so whether we will reject the null hypothesis or not reject the null hypothesis. That depends on something that's called the p-value. And this is now a little bit of new information that we haven't discussed yet, but I would like us to introduce this concept in this lesson, so that by the next lesson, when we investigate p-values a little bit further, we are already familiar with the term. So for our pair t-test, we're going to look if the p-value is bigger than if the p-value is bigger or smaller than 0.05. 0.05 is the alpha value, and that is the default alpha value. That is, in actual fact, our default confidence interval or our p-limit. And if the p-value is smaller than 0.05, we reject the null hypothesis. But if the p-value is bigger than 0.05, as is in the case of this example, it's 0.2992, so it's not smaller than 0.05, then it means that we cannot reject the null hypothesis. So we cannot say in this example that there is a difference between the systolic blood pressure before and after the intervention took place. Then another piece of new information, and don't worry if you feel like I'm moving a little bit faster today. As I've mentioned just now, I'm merely introducing these concepts, and we will go over them in the next lesson. So that is called normality tests. We are conducting a t-test because the sample is small. We aren't sure if the data is normally distributed or not, so we need to look at a normality test in order to determine that. And there are certain plots that we can look at that will aid us with this decision, and certain tests that have been developed in order to help us determine if the distribution is normally distributed or not. One of these is called the QQ plot. And this is how the QQ plot looks. So with a QQ plot, we have to investigate the data points around the line. And if there are any extreme outliers, then the t-test might not be valid, because when we're conducting a pair t-test, we're making 4 main assumptions. The first assumption is that the dependent variable must be continuous. The second assumption is that the observations need to be independent of each other. That is the case in this example. The observations denote that of 12 men's systolic blood pressure taken before and after the stimulant is given. The male patients are definitely independent of each other because the measure are not of the same patient. And then the third observation we make when we're conducting a paired sample t-test is that the dependent variable should be approximately normally distributed. And that is what we've confirmed now. And then lastly, the dependent variable should not contain any extreme outliers. So apart from the QQ plot, we can also investigate normality with a proc univariate statement. Now with this statement, we can investigate a test called the Anderson-Darlington test. If the p-value of the Anderson-Darlington test shown is smaller than 0.05, that is also an indication that the distribution is not normal. It defies the normality assumptions. If that is the case, then we cannot use the pair t-test. We will need to either transform the variable first or come up with a different approach because the t-test results might not be trustworthy. But in this case, the goodness of these tests show that all the p-values are bigger than 0.05, so we don't have to worry about violating the normality assumptions. And that's how you conduct a pair t-test in SAS for a small sample. In Module 2, you can expect to breach the gap between descriptive and analytical analysis. These will include some regression techniques like linear and logistic regression. And of course, we will stock up on more tricks for our SAS Studio toolkit. I hope you'll be joining me for Module 2, as Module 1 was but the building blocks you need to become an analytical expert. The 5 practical skills that we're developing in the Probability and Statistical Analysis course include the fundamentals of stats, exploratory stats, inferential stats, statistical programming, and the presentation of results. Congratulations on embarking on this journey, and have a look at the skills you've acquired so far. This is still just the tip of the iceberg, as in stats, you never stop learning. But thus far, you've made some major improvements towards understanding descriptive statistics, estimation, hypothesis testing, and SAS Studio better. We'll continue to check in with you on your progress for the rest of the course. Keep it up. Congratulations, you have successfully made it to the last topic of the day. We're now going to end this module on a high note and cover a variety of concepts in the next SAS Studio demonstration. In Lesson 1, we learned how to import data and how to conduct some basic statistics on the data. Throughout this module, we've learned how to use the transform data function. We've learned how to use the bar chart, the histograms, and we've learned how to use the functions of summary statistics t-tests. For the last demo of the day, we can do some recapping of everything that we've learned by adding some new tips and tricks that we haven't touched on yet. Let's first recap how we can import data. So here at the top, click on Options. Then you click on New Import Data and select the data file you want to import. And if you remember in our My Folders folder that we created in the SAS University Edition folder, we imported the wine quality dataset info. And then from there, once the file or the dataset that we wanted to work with was in our My Folders folder, it appeared in the My Folders location in SAS Studio. So when we click on these funny little dots and we select the dataset, that is how we imported an Excel file into SAS Studio. Then we click on the Running Man icon, and SAS created a temporary dataset called Work Import in the work library of SAS Studio. Other files that we also import into SAS include CSV files, Microsoft Excel files, some SPSS files, and Stata files. Now that we've gone over the basic steps of importing a dataset, I'd like us to have a look at how we can join two datasets when there is a common variable in the dataset, like an ID variable, whereby we can join the two datasets. I've created, with the help of an Introduction to SAS University Edition, two datasets named ID name and grades. The datasets both contain the IDs of students. That is this first column. The first dataset also contains the name of the students, and the second dataset, grades, that contains IDs and the grades of the students ranging from grade 4 to grade 6. So this is the 4th grade mark, and 5th grade mark, and the 6th grade mark. If we run this code, in the temporary library work folder, SAS has created two tables, grades and ID name. And now, if we want to combine these two tables, we can do that by navigating back to the server files and folders and selecting New Query. Okay, then from the new query, we drag in the two tables we've just created, grades and ID name. That is in the temporary work folder. And now we want to join these two tables by the ID column. The ID column is the column that they have in common. The way that we join the tables is by clicking on the plus, clicking join, and then selecting the two tables. The first table is ID name and the other table is grades. We will join the table with an inner join. The inner join is the most common way of joining tables. And if you now click on save, you'll see that the diagram indicates to us how the inner join works. The inner join matches the IDs to each other, and all the information that is then not in the other table is added as an additional column. So if we navigate to columns and we create the new table by selecting all the columns that we want to include in the combined table, we select ID and name from the one table and ID and grades from the other table. And then we can name the new table, combined table, and run this statement. Now we note in the output data that there is a table containing the ID name and the grades of the students. So this is actually a duplicate column we can remove, but you can see that it matched each ID of the first table with the IDs of the second table. So let's just remove the second ID column. There we go. Now the dataset contains the IDs, the names, grades, and scores of the students. And that's how you can join two tables in SAS Studio with a common variable. And now for the last part of our demo for the day, we can navigate back to the red wine dataset that we imported earlier. We can recap how to create graphical displays from this dataset, just to make sure that we're 100% familiar with how the process works. Navigate to Tasks and Utilities in your left-hand side pane. And you scroll down to Tasks. You can navigate to Transform Data first. If you remember, we saw that variables in this dataset was a bit skewed. So we wanted to transform some of the variables, and we used the transform data function to do so. So let's select one of the variables. Let's choose a variable and work with that and transform it to get it more normally distributed. In order to do that, we need to first create some summary statistics. So we need to create some histograms, and we will work with the work.import dataset. Select all the columns from that dataset. Then we need to specify that we want to include skewness and kurtosis, as well as the histogram and box plots. Okay, now that the statements are executed, we note that the chlorides variable has an extremely high kurtosis. If we navigate down to chlorides histogram, the distribution looks very skewed. There is a tail to the right. So let's look at transforming this variable and alter the variable closer to the normal distribution. By the way, if you're wondering what chlorides is, it's the amount of salt in the wine. And the reason why I'm choosing to transform this specific variable is because the kurtosis is extremely high, like mentioned. If you remember from prior lessons, we typically compare a variable's kurtosis and skewness to that of the normal distribution. The literature states that a kurtosis of less than 3 or more -3, so between -3 and 3, is mesokurtic. So it's more like that of the normal distribution. And a skewness factor of between -1 and 1, according to some literature sources, resembles that of the normal distributions. But remember, we need to also take into consideration the shape of the distribution. You always investigate how the data is distributed, as well as look at these skewness and kurtosis values. Let's now transform the chloride variable to see if that can help make the variable more normally distributed. We navigate back to the tasks and utilities in the left-hand side pane, and we click on Transform Chlorides variable. We will log transform this variable, meaning it is multiplied with a natural logarithmic formula. That transformation will create a new variable called log chlorides. We've now created a new variable, so what SAS does is it adds the log chlorides variable to the dataset. And now we can conduct summary statistics again to compare the transformed variable. We select the chlorides and transformed chlorides variables so that we can compare the two. And let's include a histogram with a normal density curve superimposed. Oops, I forgot to include the summary statistics. We want the skewness and kurtosis selected as well. Okay. So we can clearly see the transformation already made a big difference in these values. The skewness was 41 before the transformation, and after the transformation, the kurtosis is 9. The skewness was 5, and after the transformation, it's sitting at 1.7. So looking at the graph, that is our untransformed chlorides graph. We note that the superimposed normal density curve over this histogram indicates that there's a lot of outliers in the untransformed variable's distribution. And we note that the peak is extremely high. And then log transforming the variable seems to help a lot to make this variable's distribution more normally distributed. It looks much more normally distributed now after that we've log transformed it, because the distribution more closely follows the normal density curve. And that's it. Have you secured your place already? Remember, time is running out, and you have to give yourself enough time to complete your courses comfortably. Take out a 6 months or a 12-month membership to achieve your goals. Shaw Academy continues to be really committed to bringing higher education at a lower cost. We frequently run specials where you can get as much as 50% off our memberships. So make sure you contact your student advisor to discuss our offers and ensure you're signed up for your spot on Module 2. Remember, Module 1 covered all the fundamental basic concepts for your analysis journey. Module 2 will cover immediate concept. Thereafter, Module 3 will be advanced, and Module 4 proficient. And this brings us to your 4th weekly assignment. I strongly encourage you to complete the end of lesson quiz as well as your weekly assignments, as they will prepare you for the final module assignment. And that brings us to the end of Module 1. See you soon for Module 2, Lesson 1.